our plan for today. So first, we're going to be talking about using data to improve ecological forecasts. And this is part of the Macrosystems EDDIE program, which is a program that is currently working on teaching ecological forecasting to undergraduates. And I'll talk more about that in just a second. But first, our schedule for today, we have a few minutes set aside for welcome and a schedule overview and a quick icebreaker question to understand a little bit better what your goals are in joining the workshop today. And then we'll spend just a few minutes introducing the EDDIE and Macrosystems EDDIE educational programs for undergraduates. We'll then, since I noticed that many people did not yet have the chance to complete the module pre-assessment, we're going to give all participants several minutes to complete that during this time. If you have happened to complete the assessment already, this would be a time for you to explore the teaching and instruction materials associated with this module and the other Macrosystems EDDIE modules to give you a few minutes to think about whether they could be useful in a class that you teach or for your own research. We'll then have a short 25-ish minute introductory presentation on using data to improve ecological forecasts, how we do that and what it means, and then a break. When we come back from the break, we'll begin working through the module. So for the first hour, we'll be working on the first two components of the module where we select a lake site to work with and explore the data at that site and then complete the first of the three parts of the module. We'll then discuss that a little bit, have another break, and then complete activity B. And then end with a little bit of discussion after activity B and then do the module post-assessment and wrap up. There is an activity C associated with this module that I haven't scheduled in time for today because I didn't want to be overly rushed, but that is something that there is the opportunity to explore if you finish activities A and B a little early. Okay, any questions on the schedule before we move into our icebreaker survey? Okay. So this is our survey, and I'm going to go ahead and stop sharing and open our Zoom poll for this. And our question to you is, what are your primary goals for attending this workshop? And you can check any of the choices, as many of them as apply to you. And so we'll just give you a minute to think about that. Okay, so this is what folks shared as sort of what they were hoping to get out of the workshop today. And so this is really cool because to me, it illustrates that there is some interest in learning more about Macrosystems EDDIE in general. So maybe some people that are interested in teaching a module in their class, but also a lot of interest in just learning more about ecological forecasting, including ecological forecasting for research, which I think is great. And I think this will be a really good opportunity to do this because by completing the module, you will be learning about the process of data assimilation or using data to improve ecological forecasts. So that's great. I think we're on track, and that's just helpful for me to know and keep in mind as we're going through the workshop so that I can hopefully tailor things or fit things to meet your needs as best as possible. Okay. So I'm going to close that and we'll get back into this. Okay. So I'm going to spend just a few minutes briefly introducing the Macrosystems EDDIE program. And so Macrosystems EDDIE fundamentally, in its current version, is focusing on providing ecological forecasting materials and teaching materials for undergraduates. So while there are educational materials available for graduate students primarily in ecological forecasting, we were really interested in thinking about how to reach the undergraduate population. And so our goal is to introduce forecasting by doing hands-on interactive materials that are approachable, not just for students, but also for instructors who may not have previous training in ecological forecasting either. And I just want to point out quickly that Macrosystems EDDIE falls under sort of the umbrella or the larger project of Project EDDIE, which is Environmental Data-Driven Inquiry and Exploration. And there are several sort of different projects within the larger Project EDDIE. The one that we're talking about today is EDDIE Macrosystems, which are a series of grants at Virginia Tech in Blacksburg, Virginia, USA. But we definitely encourage you to check out the other EDDIE projects as well. What all EDDIE modules have in common is that they are designed in this sort of three-part structure. They use real, messy environmental data to help students develop quantitative reasoning skills, and they're all designed to be hands-on and interactive. And they're designed both by sort of the leaders and principal investigators of the project, but also by instructors, sort of crowdsourced to develop these modules. And so there's a QR code and a link down at the bottom of the slide if you'd like to learn more. Macrosystems EDDIE specifically, the goal is to teach both local to continental scale ecology. And so our overall objectives are to help students develop and test hypotheses about complicated effects of global change using ecosystem models, some of which are sort of research grade, many of which are kind of research grade ecosystem models, as well as to learn basic computer programming in R. And then sort of specifically to the ecological forecasting modules, which is what we're doing today, instead of programming in R, you're going to be using an app, so like a friendly user interface with R code under the hood to help teach key concepts in ecological forecasting. So some key features of EDDIE modules, if there is someone who's interested in applying these in their classroom, is that each module comes with a lesson plan and a PowerPoint that is ready for the instructor to use, as well as recommended pre-class readings, in-class activities and data sets already provided, and homework and answer keys. And so all of that is available to you as the instructor. The overall learning objectives, as I briefly mentioned, of all EDDIE modules, including Macrosystems EDDIE, is to build these quantitative skills using real environmental data, and particularly larger data sets, because we know that that's more and more often what students are going to need to be able to wrangle as we convert ecology into a censored science. And also to develop the ability to visualize and interpret these real environmental data. So to date, our team has developed 8 Macrosystems EDDIE modules. The first 4 are focused in R, and so they're using an R coding interface and are focused on core concepts in macrosystems ecology. And the second 4, which I've highlighted or bolded here, are the ones that are focused on ecological forecasting. And we will be doing module 7, using data to improve ecological forecasts today. All 4 of these modules are delivered through a Shiny app. And so once you've sort of seen what module 7 looks like today, you'll have a really good sense of what the rest of the modules sort of look and feel like in terms of the interface that students will see as well. Okay, so that's a very, very brief overview. Oh yes, thank you, Kaylin. Yeah. Please do reach out to us if you have any questions about any of the other modules, because we would love to talk more about kind of what's included and what they offer. Okay, so with that, I think we're going to move into giving you all an opportunity to complete the pre-assessment for the module that we're working on today. This is optional. You're not required to complete it, but the reason that we're asking you to do it is because this is incredibly helpful for us to assess how well the modules that we're developing are actually meeting the learning objectives that we're trying to teach. And so by completing a short assessment both before and after the module, we can assess whether we are actually teaching the concepts that we want or whether we're missing the mark a little bit. So this link is provided to you in the email that you received from me. I'm also going to drop it into the chat right now so that you can have it there. Or there is the QR code if you grabbed that off the screen. And I will show, thank you, Curtis, for asking that. I will show the ID numbers in just a second. So let me get back into the PowerPoint so that you can see that. And no, I saw that there were 2 people that had already filled it out, and you all both use student IDs that are not repeated here, so it shouldn't be a problem at all. And thank you for doing that ahead of time. That was what I was hoping that some folks would do, so thank you for that. So if you are in the room now, we've just sort of randomly assigned ID numbers, and it will ask you for a student ID number when you log in to take the pre-assessment, and you can use the ID number next to your name. So I'll leave this screen up for a couple of minutes until folks get situated. And then if there's anyone, there is at least one person in the room who has already completed the assessment, I'll flip back to the previous slide so that you can get the link to the module landing page and look through the materials if that is of interest to you. So we'll take about 10 minutes to let people work through the pre-assessment.
Should we pause the recording for a bit, Mary?
That's a good idea. Let's do that.
Yeah.
Thank you for reminding me. And then we'll get into the module. Okay. So an overview of what we'll be working on today. We're going to briefly introduce the concepts of ecological forecasting broadly, as well as how we measure forecast accuracy, the concept of uncertainty in ecological forecasts, and then specifically the focus of today is data assimilation. And so there's going to be 4 parts to this module, and we'll be completing the first 3 today. And if we have extra time, we'll do activity C, but my guess is that we will probably not have extra time. We'll see. So the first 3 parts that we'll be completing is you'll do a site selection where you will access and explore data from a lake of your choice that is part of the National Ecological Observatory Network in the United States. And I'll talk a little bit more about that later in the presentation. And then in activity A, you will use data from that site to build a very simple ecological model and generate a forecast of ecosystem productivity, which is going to be represented by chlorophyll A for the context of this module. In activity B, you will then explore how updating your model predictions with data as they become available, like newly observed data, affects forecast accuracy. And not just the effect of assimilating that data, but also the effect of how much observation uncertainty is associated with those data on forecast accuracy and how often the data are collected. Okay. So the larger motivation behind development of these educational materials is that ecosystems, as we all know, are changing worldwide as a result of climate and land use change. And so we are seeing across both aquatic and terrestrial ecosystems, human pressures that are affecting primary productivity. And as a key provider of ecosystem services, lakes and reservoirs are particularly important to understand, and we are interested in knowing how they'll change in the short term to help manage them for things like water quality, safe bathing and recreation, and so on. And so ecological forecasting is a potentially really powerful tool to help lake managers preemptively prevent or mitigate water quality concerns. And so this is why we forecast. So before we start, I just want to briefly make sure that we're all on the same page about what we mean when we say a forecast. For today, we are defining a forecast as a prediction of a future event with uncertainty. And so some key points in this definition include the event has not yet occurred. So we really do not know what's going to happen. We give a probability or a likelihood of the event to occur. That's the uncertainty, just like when you look at your phone and check the weather forecast maybe, or see the weather forecast on TV or in the paper or whatnot. There's a percent chance, and that's the uncertainty of the forecast. And also a forecast, importantly, should be actionable. And so what do we mean by that? Actionable means that with the information provided in the forecast, someone could take an action or make a decision with that information. And so the list of things that we forecast on a daily basis in human society are quite long. Here are just some examples. I'm sure the folks in this room could think of more. Everything from weather to forest fires, greenhouse gas emissions, election results, sports, may be relevant for some of us with the World Cup this week and going forward, transport, what traffic is going to, when and where traffic is going to be heavy, and much more. And the purpose of a forecast can potentially be twofold. First, a forecast can allow you to prepare for an upcoming event. A good example of this would be a weather forecast, such as a hurricane. Nothing you do is going to change the path. Nothing you do as an individual, obviously, is going to change the path or the severity of a hurricane. However, the forecast allows you to prepare your home, to evacuate if needed, and make other preparations for that event. The other potential purpose of a forecast is to allow you to take action that could potentially even change the trajectory of the forecast. And so an example of this would be disease forecasting or fire forecasts. If you have a forecast of where a fire is going to travel, you can deploy firefighters to that area, and that action may in fact change the outcome of the forecast. Importantly, forecasts should specify some uncertainty around the prediction. Inherently, forecasts are a guess of the future, hopefully a well-informed guess of the future, and therefore it will always be uncertain because we cannot know what the future holds. Uncertainty is a really important part of how people evaluate risk and make decisions. A good example is, again, going back to that weather forecast. If you see there is a 20% chance of rain versus an 80% chance of rain, you will probably make different decisions about what you wear outside on that day. And typically, we see that uncertainty increases with time into the future. And this makes sense to us. We are more certain about what the future might bring tomorrow than we are about what it might hold next week or next month or next year. And so it's really important for us that forecasts include some quantifiable, some quantitative numeric measure of uncertainty. When we're thinking about ecological forecasting, we can think about forecasts being produced iteratively over and over again, just like a weather forecast is updated every day. And this iterative production of forecasts we refer to as the forecast cycle. And the cycle has several steps. The first step would be to create a hypothesis about how you think the natural world works. For example, you might have a hypothesis that there is a positive relationship between future air temperatures and future water temperatures, that as air temperatures increase, water temperatures will increase. The second step is to build a model that represents that hypothesis. And the thing that I like to emphasize with students and also non-students when we talk about this cycle is that the model does not have to be terribly complex to potentially provide pretty good predictions. And so in this case, we might have some sort of very simple linear model that represents our hypothesis that as air temperature increases, water temperature will increase. We then quantify the uncertainty associated with that prediction. What margins of error do we expect to see in predictions made with our model? And once we've quantified that uncertainty, we generate a forecast into the future. We then can communicate that forecast to people who might be interested in using it. That could be a water resource manager. That could be someone who is a ship captain on a large lake. That could be someone who's thinking about going to the beach for a swim. And then we assess the forecast. The future arrives and we figure out how well we did. Did we get the future water temperature right? And then this final step is that we use that most recently observed data after we've assessed our forecast. We update our model with that data to generate the next forecast for the following day or the following week or whatever it is. And so this is what we call the near-term iterative forecast cycle. And today we will be focusing on the components of the forecast cycle that are highlighted here. So we'll build a model, we'll quantify uncertainty, generate a forecast, and then importantly, we'll really be focusing on that piece, on that part of the cycle that is updating our models with the most recently observed data. Okay, so again, just to make sure that we're all on the same page, when I'm talking about an ecological model, I simply mean some sort of representation of a real phenomenon that is difficult to observe directly. And our goal in building the model is to understand and predict that phenomenon. And so we might have a goal of predicting chlorophyll A concentrations in a lake, and our model could be as simple as a linear regression. Maybe one example could be that as phosphorus concentrations in a lake increase, chlorophyll A will increase. And an important point is that models are imperfect representations of really complex ecosystems, which I think is very intuitive to all of us here in Gleon, that lake ecosystems are incredibly complex and no model is going to perfectly represent everything that is happening in a lake. And so models for ecological forecasting are imperfect representations of the ecosystems that we're trying to forecast. And so our goal with our module today and what we're trying to teach is thinking about how do we make sure that the model lake resembles the actual ecosystem as closely as possible. We want to make sure that that digital lake in your computer as closely matches the real lake outside as we can. And so the way that we're going to be thinking about doing that today is by updating our forecasts with as recent of data as we can when those data become available. And so that process is called data assimilation. It's just the process of updating models with new data. And in ecological forecasting specifically, data assimilation would be the process of updating ecological forecasting models with new environmental data as they become available. And you can see an example of what data assimilation means in terms of forecasting in the graphic at the bottom of the slide. So this is a graphic that's showing multiple forecasts of Hurricane Irma, which occurred several years ago in the Gulf Coast. And each purple cone represents a separate forecast of the hurricane's trajectory, with the central tendency of each forecast shown in yellow and the actual path of the hurricane shown in red. And what you can see is that over time, as the hurricane moved through the ocean, the most recent data regarding the position and severity of the hurricane were used to update the model that was producing the forecast, which is why you see lots and lots of purple cones sort of overlapping each other through time. And so this is hopefully a very familiar example of how data assimilation is used in a place that you've seen before. And so the key component, what we're doing when we assimilate data, is that we're using the recently observed data to update the initial or starting conditions of our ecological model. So in general, forecasts are generated using the most recent observational data or something very close to it as the initial condition for the forecast. And then new data are used to update that. So what that might look like is that we have some data on the plot on the right. We have a time series of chlorophyll A, and we use that most recent observation in the gray circle to inform some initial condition or starting condition for our forecast. And then we generate that forecast out into the future with uncertainty. When new data become available, so in this case, the new data are shown by the black circle, we use that new data point to update our initial condition. And then that new initial condition is used to generate a new forecast into the future with uncertainty. And hopefully that new forecast is more accurate than it would have been if we had not been able to update our model with that data point. And another important point about data assimilation is that when we are using our observations to update our model initial conditions, the way that we, or how much we adjust our initial conditions based on the observations depends a lot on how certain or uncertain those observations are. So what does that mean? So in the example on the left, we have a time series and then a forecast that's been generated into the future. And then if we were to observe a new data point that is kind of outside the predictive interval of our forecast, if we have low observation uncertainty around that data point, meaning that we're very confident that that observation is a good one that closely resembles the real state of the ecosystem, we're going to update our initial conditions quite a bit to try and get as close to that observation as we can to generate the next forecast. And that makes sense. We think this is what's really happening in the ecosystem, so we want to update our model to like closely match that. If, on the other hand, we had a situation where we had a new observation, but we were really uncertain, like we don't have a lot of certainty in that observation. And an example of this might be, for instance, like a phytoplankton count under the microscope, where, depending on who's counting it, there can be a lot of variability in between different counters, for example. We might have a lot of uncertainty in that observation. And so in that case, we might not adjust our initial condition as much because we have maybe as much confidence in the model as we do in the observation. The observation isn't providing a whole lot of additional information to us. So I'm going to stop there for just a second, because that is a concept that people often have questions on. How is that resonating with folks? Does that make sense that the degree of observation uncertainty affects how much you adjust the model? Maybe give me a thumbs up or similar. Yeah, doing okay? All right, sweet. Thank you. That helps me to just keep track of how we're doing. Okay, and so then probably I think the final key point that I want to make here about sort of how data assimilation works is that, and maybe this is self-evident, but we can only update our models with data when data are available. And so obviously that availability, how often we have data to update our models, is affected by data frequency and data latency. So what does that mean? Data frequency simply means how often data are collected. Is it something where you've got an in situ sensor that is collecting data every 10 minutes and streaming it to the cloud so that it can be automatically updating your model? Or is it something where someone is taking a 3-hour hike out to a remote lake once a month and collecting that data point? So that would be data frequency. And then data latency, a very similar related concept, is the time between when an observation is collected and when it is ready to be used in a forecast model. So in the example of the automatically streaming sensor, the data may be available very, very shortly after it's collected. However, if you have an in situ sensor, it might be collecting 10-minute data. But if you can only get those data when someone travels to the lake and downloads the sensor, the latency on that data can be quite high, because there's a fair amount of time between when it's collected and when it can be brought back to a computer and incorporated into an ecosystem model. And so both of these things, the frequency and the latency of the data, can affect how often we can assimilate data into our forecast and update it. And so in the example that I'm showing here, we have a forecast that really, did not successfully capture the next observation. And the question becomes, could we have better captured that black circle in our forecast if we had more data to inform kind of the trajectory of the ecosystem in between that we could use to update our model? Okay, so today we're going to use the model to generate a forecast of primary productivity in lakes, and then we're going to use real data to update this model via data assimilation. And so our focal question is, how can we use data to improve ecological forecasts? And so I think for many of folks in the room, this is something that we're very comfortable discussing, but I just want to remind people, and also because if you are an instructor, this is sort of the presentation as we would deliver it to students, that there are several drivers of primary productivity in a lake, including light, water temperature, nutrients, phytoplankton, and zooplankton, and probably more that you can think of that are not listed here. And all of these factors interact to control primary productivity. For the purposes of today, we're going to be using a very simple primary productivity model. I really think that this is a strength of the module, that it's a very simple model that a student can be introduced to and understand all of the components of within a fairly short 3-hour time span of the activity. And so in this simple model, you have sort of 2 state variables, which would be the variables that are shown in the green boxes: producers, which are phytoplankton, and nutrients, which for purposes of today will be represented by nitrogen. And the reason that we are using nitrogen and not phosphorus will probably become clear when we start to dig into the data that is available from the National Ecological Observatory Network. In this model, producers take up nutrients and grow, and if they die, the nutrients in those producers are released back into the water column. And then in addition to incoming light, the growth of the producers is also influenced by water temperature. So those are sort of the 2 model drivers that we have: sunlight and water temperature. For today, we'll also be using data from the National Ecological Observatory Network, which is a continental scale network across the United States. There are 7 different lake sites within the National Ecological Observatory Network, or NEON, and we'll be forecasting productivity. You can choose which of those lake sites you'd like to work with for the activity. The nice thing about these NEON data is because they're collected in a standardized way at every site, you can compare across sites really easily, and that is a really powerful tool for sort of ecological understanding. The learning objectives for today: hopefully, at this point, you have already met the first one. You might be able to give your own explanation and define data assimilation. We are also going to generate an ecological forecast for primary productivity, describe how to assess ecological forecast accuracy, which we'll talk a little bit more about in the module, describe how data assimilation affects forecast accuracy and uncertainty, and then explain how updating models with data collected at different timescales, for example, daily data versus weekly data, and with different levels of associated observation uncertainty, affects those ecological forecasts. So we're about to go to break, but when we come back, these are the 2 parts of the module that we'll be working on. We'll first be working on site selection, and we'll be sending you into breakout rooms so you can decide whether you want to work with a partner, as is suggested here, or whether you'd like to work together as a small group. Together, you all will select a NEON site, and I might ask that I may do a little bit of nudging to try and get people to pick different sites so that we all don't end up doing the same lake, because it tends to be more interesting if different people work on different sites. So select a NEON site, visualize the data at the site, and explore relationships amongst the data will be the first piece. And then in activity A, we will build that simple ecological model and use it to make a forecast. So that's where we're headed. When we come back from the break, I will talk you through the Shiny app, but in the meantime, I will leave this slide up so that you can start to navigate to it if you would like. And this is the link for the app, and then we'll kind of go through all the functionality when we come back from break. And Whitney, thank you for putting that in the chat. So at this point, I'm going to stop sharing and see if anybody has any questions before we head off to our first 10-minute break.
May I ask a question, Mary?
Please. Yes.
Yeah. I saw from the picture you showed, you took the graph and you took the observations always still. Let me try to rephrase that word. So I from some other way I heard this another option to, instead of still use the initial state within the uncertainty range of your forecast, rather directly from observation. Then for that strategy, what is the drawback?
Yeah, so that's definitely a very valid way of doing data assimilation. So if I'm understanding properly, you're asking, why do we not just update the initial condition to be exactly our observation?
Yeah.
Yeah, and that is a way that you can do it. So I don't want to suggest that you can't do that. The drawback would be that it isn't accounting for the uncertainty in the observation or the confidence that we have in the model in the same way. So the nice thing about the way that we're doing this, which under the hood is a technique called an ensemble Kalman filter, and I can put some resources in the chat for folks who are interested to learn more. The benefit of that is that it does account for the uncertainty in both the model and the observation. So we're able to sort of take that into account.
Yeah, because
yeah,
if I may follow up, like if saying the frequency of the observation is quite low, that you expect more accumulation of your uncertainty for your forecast, and then the deviation might be also far away, then how confident you are about the model forecast after a long time would be.
Yeah, and that's a potential drawback. So if you have to be, when you're thinking about applying this method, you do have to be careful to make sure that you are maintaining a good amount of variance or uncertainty in your forecast. If your forecast becomes too confident and wrong, then that would be a time when you could get into trouble by using this approach. But the benefits would be that you are able to account for both the uncertainty in the observations and the model, and also that you can use this technique to update your model parameters and things that are like states in the model that are related to the observations that you have indirectly, using the relationships between the observations you have and the states that you haven't observed. So for example, if you are trying to model water temperature at multiple depths in the water column, but you only have an observation at 1 meter depth, with the ensemble Kalman filter approach, and again, I'll provide a little more information about that in the chat. With the ensemble Kalman filter approach, you can use that observation at 1 meter to update your water temperature at 2 meters, at 3 meters, and so on. So you can use it to update things that you haven't actually observed directly. But you've identified one potential drawback, which is if you get in a situation where your model is overly confident and very wrong, then you can get yourself into trouble with this approach.
Okay, thank you for your explanation.
Thank you. Yeah, and I'll provide some more information in the chat for when we come back. I think we are due for a break now, and we're going to take a 10-minute break because I think people need that when we're on Zoom. So we will come back at 10:04, and at that point, we'll get you guys into Zoom rooms and start working on the module. So welcome back, everyone. And I just wanted to briefly, I actually wanted to briefly address Ching's question in a little bit better now that I have this graphic pulled up, which is part of the module. So I just want to share with you guys, there are actually 2 versions of the introductory PowerPoint that you just saw. You saw the one that is designed for students who have not completed any of the other Macrosystems EDDIE modules. There's also one that is for students who have already completed 1 or more other modules. And therefore, we assume that we can go a little bit more in depth with that version. And this is a slide that briefly introduces the ensemble Kalman filter for folks who were not familiar with what we were speaking about right before the break. And so this is the technique that we're actually using for data assimilation under the hood for this module. So the way that this is very briefly working at a high level is that the ensemble or the multiple model runs are initiated using the initial condition, which is marked by the black X. And so multiple versions of the model are run with that initial condition to generate a forecast for the next time step, which is represented by the shaded oval. And then you have some observation, which is represented by the circle, and that observation is used to update the initial condition. And importantly, what Ching was talking about is that here, the observation is outside the range of uncertainty that is predicted by the model ensemble. And so one one thing to note with this particular technique is that it's not going to update the ensemble to some value that is outside the range of possible futures that the ensemble has predicted. So we're not going to end up with an initial condition that perfectly matches our observation. We're going to end up with an initial condition that is somewhere between what the model thought was the most likely forecast and the observation that's represented by the X here. And then we generate a new forecast for the next time point. So that's a really high level overview of how the ensemble Kalman filter works. I just wanted to make sure that we didn't lose people who maybe weren't familiar with that before. And if you're interested in learning more about it, because a lot of people in the poll did say they were interested in using ecological forecasting in their own research, I've dropped a few papers in the chat. The first one is a nice overview of the ensemble Kalman filter, and then the second two are both examples of this being applied to a lake. With the third one, the near-term iterative forecasting system being, an iterative real-time forecasting application. Okay, any other questions on that before we dive into the Shiny app and get moving? Okay, so I'm gonna briefly share my screen so I can give you an overview of the app and its features before we go into breakout rooms. So when you click on the link for the Shiny app, you should get to a homepage that looks like this. This is, and thank you, Whitney, for having dropped that in the chat a couple of times. I really appreciate it. You're going to get to a homepage that looks like this. A couple of key features. You can navigate the app in two different ways. You can navigate through the app by clicking on the tabs at the top of the page. And in some cases, there will also be like sub-tabs down here that you can click through, or you can navigate through the app by scrolling to the bottom and, clicking the forwards and backwards arrows, and those will automatically take you to the next step. The first page is an overview of the activity, which we've gone through already. The second tab is some key slides from the presentation that you just saw and a little bit of a recap from that presentation in case that's helpful to you. And then the introduction is the first page where you will actually enter any information, and all that will be is your name and the ID number that I have provided for you, and then a couple of kind of questions to just kind of get you thinking before we get started and sort of help you think about the concepts that we just talked about in the introductory presentation. And a couple of other features that I want to highlight here, which can be particularly useful for instructors, is that there is a list of questions, well, students and instructors, there's a list here of questions that are still to be completed within the app. And this list will automatically change as you fill in answers. So if you were to answer question 3, for example, it would disappear from this list. So it helps you keep track of what you still have left to complete in the app. And then when you are done, you can generate a report, which comes out in the format of a Word document, and instructors can use that for assessment purposes if they would like to. If you, because this is a web page, and typically when you refresh a web page, you don't, it doesn't necessarily like repopulate your answers automatically. If you need to go away and come back and pick up where you left off, instead of completing this in one session, we have a feature where you can save your progress, and that's this button down at the bottom here. And so if you click on that, what it will do is it will download this little module 7 answers.eddie file to your computer. And then when you reload the app and want to resume your progress, you can go to this area of the screen up here and click browse, and that will open up, which I don't know if you can see the pop-up when I'm sharing my screen, but that opened up my downloads folder, and I can navigate to the .eddie file and re-upload it to the website. And if I've answered questions, those answers will repopulate in the boxes where I answered them. I really recommend that you guys do that regularly. There will be prompts as you go along suggesting that you save your progress, and all it requires is for you to just click this button and download the file. And then if you don't need to re-upload it, your internet connection is good and you're able to complete the app all in one go, then no problem. But if, you know, somehow your modem got reset while you were working on this, it would be a bummer to have to start from the beginning. So we just suggest that you save your progress often. Another important note for this is that for the purposes of kind of bandwidth on the server side, if you leave this idle for 10 minutes or more, it will automatically kind of gray out and disconnect. So if you know that you're going to step away for more than 10 minutes, we definitely recommend that you save your progress before you leave. As you go through the app, you'll see that there's different questions to answer. You can pick the site that you would like to work with and view the latest PhenoCam camera image of that site. It looks really cold in Wisconsin today. So if there's folks who are in that area, more power to you. And you can also, as you go through, type answers in to the boxes and so on and so forth. You'll create plots. The plots are all in Plotly, so they're interactive. So for example, if I select air temperature, I can sort of zoom in or select data and kind of play around with the plots interactively that way. Okay, so what we're going to be getting started on right now is the site selection part of the app, as well as activity A. And then when you get to the end of activity A, which is the end of objective 6, we're going to give you about half an hour to work through this, maybe 35 minutes. And then we'll bring you back from your breakout rooms into the main room, and we'll have a few discussion questions and sort of see where people are at. Are there any questions before I open up breakout rooms? I'm going to put you in groups of 3 to 4. And Kaylin, do we want to assign lakes or do we want to let people choose? Yeah, have everybody do different lakes? Okay, cool. Any questions before we assign lakes and go to breakout rooms? Okay, so I'm going to, let's see. Let's do, we have 18 people. So I'm going to do, I think, 5 breakout rooms. Let's do breakout room 1 is going to be Crampton. Whoops, sorry. Room 2. The question we had was sort of about data availability from the neon lakes and the fact that there's like a lot of, that there may be substantial gaps in some of the data sets. So a couple of factors that are contributing to that. First, at some of the lakes, those buoys are coming out in the winter, which makes sense because they freeze in the winter months. And so we're trying to avoid sensor damage by removing those buoys. Second, I believe that the time series that you're looking at correspond to also sort of the beginning of the NEON program, when there was a lot of kind of troubleshooting and QA/QC and calibration that was going on with the sensors and buoys at some of the sites. And so you're probably seeing some gaps that reflect that process of just kind of getting things up and running for this 30-year data set that is going to be collected going forward. But one thing about that is that, you know, the fact that there's gaps in the data is actually one of the sort of teachable moments that we are hoping that students take something away from with the EDDIE modules. You know, the goal of those modules is to have students using real messy environmental data where there are gaps in the data set and there are inconsistencies. And so actually asking them to think about what that means for modeling and forecasting is definitely part of the learning objective. So that was kind of one question that we had. And one thing I also wanted to kind of add along with that is that it's been sort of cool that in developing these modules, we've also been able to provide some feedback to NEON about the QA/QC of their data, which they've appreciated and been able to sort of subsequently incorporate into their workflows. So that's kind of been a really nice, beneficial feedback loop for both us and them in terms of data QA/QC. Another question that came up was about sort of the nitty-gritty structure of the NP model or the box and flow model that's forecasting chlorophyll A. And so I have a couple of resources to point folks to if they are interested in exploring that a little bit more. And it kind of just depends on how nitty gritty you want to go. If you want to know a little bit more, you can check out the Introduction to Ecological Forecasting module, which I've just pasted in the chat, which spends a little bit more time going through the details of the model structure in sort of that user-friendly interface, like the Shiny app interface. We just don't spend quite as much time on it here because we're kind of more trying to get to the data assimilation piece. But also, if you're really interested in knowing exactly what's under the hood, we do have a GitHub repo associated with this project, and the function that contains the NP model for module 7 can be found at this link. So in general, all of the Shiny and R code can be found on GitHub, and that's available for those of you who like to work in that space. And if you kind of just want to see the couple of very simple differential equations that are going into the NP model, you can get them there. Again, this model is a teaching tool, and so this is something that we wanted to keep fairly straightforward because for undergrads, I think this is already a big ask. We're asking them to take in a lot of new information, but for this group, which is a lot of graduate students and more advanced folks, maybe those resources will be helpful for you. Okay, I also saw one more question come up in the chat. Are the chlorophyll data from lab or sensor results? And if a sensor, how are you getting the values in micrograms per liter rather than RFU? So the answer to that is that for the NEON sites, there are both lab, I believe, both lab and sensor chlorophyll A data sets. For this module, we are using the sensor data sets, and the micrograms per liter is, thank you, Kaylin. I was going to say it's done internally by the sensor, but I didn't know whether they did the local calibration or not, so that's helpful to know. Yep, thank you for that question. Any other questions about activity A or the site selection that you had that you wanted to bring up? Okay, so at this point, because we are running a little bit behind on time, yeah, thank you so much. I really appreciate the questions. They're really good. It's cool. We were just chatting while y'all were in the rooms that it's really cool to see sort of differences in what people are interested in and asking about and what they notice when we teach this with undergraduates versus with, I'll say, more advanced users. And so it's kind of fun to do that. Okay, so let's go into break. I want to honor our 10-minute break. So it's 10:57. We'll come back at 11:07 to work through activity B, or you can continue working on activity A if you didn't quite get finished. And then we'll come back at the end of the workshop for a little bit of discussion and wrap up. So I'll see you in 10 minutes. Thank you. Got through at least the first two objectives of activity B, objectives 7 and 8. We had a couple of, again, similarly, we had a couple of questions that came up as we were sort of traveling through rooms and checking with folks. And so I wanted to address those with the larger group because they were really excellent questions. There was one really good question about sort of how you assess forecast accuracy. And for this module, we are using root mean square error, which is, I would argue, it is, the reason we chose to use it is because we hoped that it would be a metric that undergraduates were familiar with, had potentially seen before in statistics classes. But I think one important point to make there is that it is not what I would ideally choose to assess a probabilistic forecast, because it is not a metric that's designed to handle kind of a probabilistic input. It only measures kind of the comparison between your forecast central tendency and the observation, whereas ideally we would be using something like a continuous ranked probability score, or an ignorance or log score is another one that assesses both the forecast central tendency as well as the spread or the uncertainty around it. So I just wanted to make that point because it was really, I thought that was a great question. And then another question was sort of like, how good is good for a forecast? And I'm sort of curious, I kind of want to open that one up to the group. How good is good enough when you are looking at a forecast? How do you know when your forecast is good enough? Because I'm not sure I have an answer, so I'm curious what other people would say.
I guess what I would say is, does it have practical meaning, in your system?
Yeah. Yeah.
So
Yeah.
we figured out thresholds that, might be important to us as far as our system operations. So does it hit that threshold? Is it, those are the kinds of things that we look at.
Right. Like if there is a particular threshold that triggers some sort of alarm or alert for a water quality perspective, and our uncertainty or our inaccuracy of our forecast is kind of ballooning above that threshold, that may not be a super informative forecast for you. Yeah.
I have just like, for me, it's really related to how good quality of your input data or calibration data. If they have a really high, smaller RMSE, and then the model result, if I say it's good, and it should have like similar smaller RMSE, really close to that the observation, and I would call this good. Otherwise, I think it's still kind of the room to improve your performance of your model. This is my opinion.
Yeah, absolutely. Yeah, and I think that it does come back to sort of the particular utility that you're trying to get out of that forecast, and what you want to do with it, and what you're comparing it to as kind of your baseline. Absolutely. Other thoughts on that? How you know when your forecast is good enough?
Has it been calibrated to the water body that you're working on? Because if you're trying to calibrate on one water body and then apply it somewhere else, what could be a good forecast in one is not going to be not be a good forecast in the other.
Right. Yeah, absolutely. Especially if the second water body has different end users with different needs, different information that they're seeking from that forecast, for example. Totally. Well,
I think maybe it's about the cost of the action that could be taken based on the forecast. So if you have, for example, you're forecasting a flood, and then that means the water authority has to basically drain a bigger amount of the reservoir and drain their expensive, good, cold water. That's a big action. And I think for that, you need a very precise forecast to take such a decision. And what you will be accepting as an accuracy for a general feeling of what's happening for the future does not apply for a very high costly action.
Absolutely. I'm glad you brought that up, because I think that's a really important point. And the forecast has to be better than whatever managers, in my opinion, it seems like it needs to be better than whatever technique for making decisions managers were using before, right? So if they have some other method that they're using, whether it's like looking at cell counts under the microscope to determine if a HAB is likely, your forecast needs to outperform that probably.
Correct. I worked once with forecasts, and whatever I delivered was worse than their practices from the knowledge of the annual averages that they had.
Yeah. It's very hard to beat climatology sometimes.
Yeah, correct.
Yeah, it can be hard to beat climatology. Yeah. Well, I'm mindful of the time, and I am hoping to provide some time here, because I really would, if possible, like folks to fill out the post assessment so we can get a sense of how we're doing with this module and improvements that we can make, because there will be a question in there. In addition to sort of the assessment questions, there will be an opportunity for you to provide feedback on the module as well. And before we get to that, I do just want to very briefly, first of all, thank you all so much for taking the time to join us today. I know this was a substantial time commitment on your part, so I really appreciate that. And I also want to just make a quick plug. If you are in a position to teach, whether as a TA or an instructor of a class, we will be testing this module that you just completed, as well as module 6, which is about understanding uncertainty in ecological forecasts, both this coming spring and next fall. And so if you think this is something that you could use with students in your courses, please do get in touch, because we work with you to deliver the modules and provide you with any kind of resources, answer questions, and so on and so forth that you might need. And I'd be really excited to work with you all, because GLION is such a great group of lake scientists and enthusiasts that would be really helpful. So with that, I just want to thank you all so much. And then I also would like to quickly drop into the chat the link for the post assessment, which we is actually pretty much the same as the pre-assessment, except for a question at the end about any feedback that you have to help us improve the module. And so if you all would be willing to spend a few minutes taking that as we finish up, that really helps us with our objectives of improving the module and having it be useful for students. But with that, I will just thank you all again. And if there's any final questions, particularly about using the modules in your class or any of the other modules, then just please feel free to address those now, or otherwise, when you're done with the post-assessment, feel free to drop off. But thank you so much.
Thank you.
Thank you.
Thank you so much, Mary.
Thank you. Thank you, Sophie.